In this lecture, I want to study a little deeper the structure of permutations. So this is lecture 1.3, and it's about cyclic structure of a permutation. Okay, so let's start. So let's take a certain permutation sigma, and I will write something quite crazy. 1, 2, 3, 4, 5, 6, 7, 8. And so it's in S8, and 1 goes to 7, 2 goes to 3, 3 goes to 4, 4 goes to 2, 7, 1, 6, 5, 8. And as we already discussed, I can draw it. So after all, the permutation sigma permutes the elements 1 to 8, and so I can see where each of them go. So 1 goes to 7, 7 goes to 1, 2 goes to 3, 3 goes to 4, 4 goes to 2, and finally 5 goes to 6, 6 goes to 5, 1, 2, 3, 4, 5, 6, 7, and 8 goes to 8. Okay, so a quick remark. So such picture in general is called directed graph. And we'll talk about graphs a little later, but a graph is a combinatorial structure which we usually picture as a bunch of vertices, so points, and they're connected by edges. And directed means that these edges have a direction. And also this one might have what's called loops, so it's with loops and multiple edges. So these guys are called multiple edges because there are 2 points connected by 2 arrows. So something interesting happens here. So if you look a little bit closer to it, so this permutation actually permutes stuff cyclically. So there is a special cycle. 1 goes to 7, 7 goes to 1, cycle where 2, 3, and 4 get exchanged, cycle where 8 goes to 8, and cycle where 5 goes to 6. So this happens in general. So if you have any permutation of any number of elements, you can understand like how decompose everything into certain cycles. So let me now explain how we do it in general. So let's define cycles. So definition. So so consider a certain collection of indices I1 up to Ik. From 1 to n, where these indices are distinct. So a cycle sigma equal to I1 up to Ik inside Sn is a permutation such that. So I will just explicitly explain what is going to what, and of course I will explain in a second how to visualize it. So if you take sigma of I sub j, one of these indices, this equals to I sub j plus 1 when that makes sense. So when j is from 1 to k minus 1. And sigma of the last one, Ik, goes back to I1. And finally, sigma of S equal to S for S not inside the set of these indices I1, Ik. So let's try to draw it in this form. So if I draw this sigma, so basically I1 goes to I2, I2 goes to I3, and so on, up to Ik, and then Ik goes to I1. So this is what I wrote here. And all the other elements got fixed. So this is a picture of sigma. just one cycle. So, okay, perfect. So let's for instance take a permutation 1, 3, 5 inside S3, and this one actually, inside S5, and this one actually sends 1 to 3. 2 is fixed because it's outside of the set. 3 goes to 5. 4 is fixed. 5 goes to 1. Okay, so some notation. So we have a couple of numbers here. So K is called the length of the cycle. And the set of indices I1 up to Ik is called the support of the cycle. And there are lots of different cycles with the same support because the cycle actually depends on the ordering of these indices, because if you reorder them, basically you will change the order in which you go around this cycle. Okay, so now let me maybe go through a few examples, and then I will formulate a theorem that every permutation is a product of cycles, like here. A very important example of a cycle is what's called a transposition. So definition. So let's take ij from 1 to n and also distinct. So a cycle ij in Sn is called a transposition. So what it does, it basically exchanges I and j, and everything else is fixed. So with this in mind, so for instance, if we take S3, so remember in S3 we had 6 permutations, and so one of them is identity, and that's of course the permutation which sends 1 to 1, 2 to 2, 3 to 3. And then there is this transposition 1, 2, transposition 2, 3, transposition 1, 3. So let me maybe say that. So I said a cycle ij. So usually people don't write. Sorry, that's fine. Okay, so these are 3 cycles of length 2. So these are transpositions. And then there are 2 cycles of length 3. And these are just all permutations in S3, so there is nothing else. So there are a couple of exercises here. So one of them is count the number of transpositions in Sn. And then there is one which is a harder one, and it's actually in the problem set. So the second one is that prove that every permutation is a product of transpositions. And why I'm talking about that right now, it is because you can think a little bit intuitively about that. So imagine you want to permute things in a certain way, and let me even maybe give you a little example. So let's suppose we have a permutation sending 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5. And doing something with it. So let's say 1 goes to 3, 2 goes to 4, 3 goes to 1, 4 goes to 2, 5 goes to 5. And then if you just look at this diagram, you can imagine how you would actually do that. So imagine these 5 elements are something really heavy, like 5 elephants, and you want to move them from position 1, 2, 3, 4, 5 into position 1, 2, 3, 4, 5, like going in this new way. And the idea is that actually, so you can first exchange 2 and 3. So you can sort of break this picture by vertical lines in a way that every moment you exchange just 2 of them. So my lines are not exactly very horizontal, but roughly like that. So on the first kind of period of time, you exchange 2 and 3, and then you exchange 1 and 3, and then you exchange 1 and 4, and finally you exchange 2 with 3. Okay, and of course, after you do it step by step, you will go from 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5 going in the other direction. So let me kind of rewrite it. So if I think in terms of multiplication of permutations, I have my resulting permutation which I want to get, which takes 1, 2, 3, 4, 5, and sends, okay, so it sends 1 to 3, 2 goes to 4, 3 goes to 1, 4 goes to 2, 5 goes to 5. But on the other hand, I can say that actually I multiply these transpositions one after another. So at the first moment, I exchange 2 and 3. At the second moment, I exchange, so now my 3 is in position here, 2 is in position here, and I exchange 1 and 3. So, okay, so after we move them, so now 1 is here, 3 is here, 2 is here, 4 is here, 5 is here, and then I want to exchange 1 and 3. So I multiply it on 1, 3. So after that, my 3 is here, 1 is here, 2 is here, 4 is here, and I want to exchange 2 and 4. And finally, I want to exchange, so now 4 is here, 2 is here, and I want to exchange 1 and 4. And from the picture, it kind of follows that this is an equality. So let's see, for instance, 1 goes to 3 here, and here 1 goes to 3, and that's it. So you just apply all this permutation to 1. So this one sends 1 to 1, this sends 1 to 3, that sends 3 to 3, and this one sends 3 to 3. And for instance, 2 goes to 4. So 2 goes to 3 here, 3 goes to 1, 1 goes to 4, so 2 goes to 4. So in this way, we presented the permutation as a product of transpositions. And from the diagram, it's kind of obvious how to do it in general. But proving it formally is a harder problem, and that's in the problem set. Okay, so I want to give another definition. So definition. So consider 2 cycles. So cycles, sigma 1, sigma 2 in Sn are called independent. If their supports don't intersect. So basically, when I apply sigma 1, I apply it to one set of elements, sigma 2 to another set of elements, and these sets don't intersect at all. So an example will be, for instance, if I have S5 and I have a permutation 1, 2 to 1, a transposition 1, 2, and I have another cycle, for instance, 3, 4, 5. So these 2 guys are independent. And the reason is because nothing intersects here. And for instance, if I take 1, 2, and I take 2, 3, 4, these 2 cycles are dependent, so they are not independent. Okay, so if you recall the picture we had in the beginning, our permutation was presented as a combination of independent cycles. So now let me prove that this is true in general. So proposition. every permutation is a product of independent cycles. That's kind of the first statement. And the second is that, so if I present my permutation sigma as a product of cycles, which are pairwise independent, a priori I can say, but like in which order? As you remember, when I multiply permutations, the order does matter. So, but actually if you have independent cycles, the order does not matter. So independent cycles commute with each other. So the order in part 1 does not matter. So again, I want to start with example. So if I take, for instance, a permutation 1, 2, 3, 4, 5, 6, 4, 3, 2, 1, 6, 5. So that looks like 1, 2, 3, 4, 5, 6. And indeed, that's a composition of a transposition 1, 2, transposition 3, 4, transposition 5, 6, and the order here does not matter. That's the same as, for instance, I can just exchange 3, 4, 1, 2, 5, 6. So how to prove it? So part 2, so proof. Yeah, just a general remark. So about rigor in the course. So all the proofs I'm going to do are rigorous, but sometimes if you want to do them very formally, that is much more work than what I do. So I kind of rely sometimes on your intuition or ability to fill in the details. And if you are not in a position to do it yet, then most of the things will appear, which I talk about, will appear in some other courses. For instance, permutations, which will appear in group theory course, and you might want to take a course in combinatorics. So you can concentrate on ideas now, and sometimes kind of the key ideas in the proof, instead of just going through all the details formally. In particular here, I'm going to explain kind of the main idea and the key technical difficulty, and the rest I recommend you to think about on your own. So, okay, so how to prove it? So part two is actually obvious. I mean, if you just take C1 and C2, which are independent cycles, then if you try to apply C1 times C2 to any number, to any index I, so then you will get basically either I, C2 of I, or C1 of I, depending on where I lies. So I is in the support. So I have no notation for it. Let me just write support of C1 in the support of C2, and this is when neither happens. And this is just a computation based on the definition of composition and definition of independent cycles. But of course that's the same as C2, C1 of I. So part 2 is more or less obvious, and part 1 is slightly less so, but the main idea is that you just take any index I. So start with any index. Any index. And then you can look where it goes. So you have I, and then you can apply your permutation sigma to move it to sigma of I, and then you can apply it again to move it to sigma of I, and you continue to do so. And then the question is, what happens? So after all, we have this picture, this graph, and we have this kind of a what's called oriented path, this edges going out. And there are a couple of possible scenarios. So firstly, this path can go forever. But that's not the case because the collection of vertices here, the number of indices, is finite. So after n moves, you have to come back, basically. Another option is that maybe after a while you will just get back to one of the points in the middle. And that's not possible for the simple reason, so sigma is a bijection. So for each vertex, there exists exactly one incoming edge and exactly one outcoming edge. And so actually this scenario is not possible, so the only way this cycle will end is when you come back to I. So maybe I can say that in the graph theoretic terms, so in the directed graph, digraph, corresponding to sigma, every vertex has one incoming edge. So like this one, and one outcoming. Like this one. And that's the reason why the cycle has to end at the end. So, so there exists certain smallest k, such that when I apply it k times, so sigma k times applied as sigma of sigma of sigma of I will return me back to I. And so this is exactly how my permutation acts on I. And so this part gives me a cycle. So I get a cycle I, sigma of I, sigma of sigma of I, and so on. And then I eventually return back to I. And that's one of the cycles. If I call it C1, then I can compose my permutation with the C1 backwards. So I can say that C1 inverse sigma, so will fix all these elements, I, sigma of I, etc. And so in some sense it's simpler. So it already fixes everything here. And then I can take any other element which is outside of the support of this cycle and continue and find another kind of cycle going from some other element and multiply on C2 inverse and so on. So eventually I get a certain presentation where I have a bunch of cycles and if I multiply all of them in this inverse powers composed with sigma, I get a permutation which fixes everything. So this is E. But then I can start multiplying on the other side and I see that sigma equals to CS minus 1 to the C1. Notice, by the way, how I'm careful with multiplying from one side or the other, because multiplication does not commute here, so I should be very careful. So that's the idea, but again, if you want to see all details, you'll listen to this proof in the permutation theory, in the group theory course. Okay, so now I have explained why every permutation is a product of independent cycles, and actually it's a product of independent cycles in the unique way up to permuting them, but I'm not going to prove it.